Imagine if you could take a massive AI model, like GPT-OSS 20 billion, and teach it new tricks in just a few minutes, without retraining the whole model from scratch. Sounds impossible? Well, it's not. Meet LoRA, low-rank adaptation, a technique that is quietly revolutionizing how we fine-tune AI models efficiently and affordably. Today, we're diving deep into LoRA, what it is, how it works, and how you can use it to make your AI models smarter without breaking the bank. What is LoRA? LoRA stands for low-rank adaptation. The concept is simple, yet powerful. Instead of updating all billions of parameters in a large language model, LoRA allows us to inject small, trainable matrices into the model's existing layers, often just the attention layers. These tiny matrices capture the new knowledge you want the model to learn. The rest of the model remains frozen, dramatically reducing memory requirements and training time. In other words, LoRA lets us teach old models new tricks with minimal effort. And the magic? It works almost as well as full fine-tuning, but at a fraction of the cost. The problem before LoRA. Many applications in natural language processing rely on adapting one large-scale pre-trained language model to multiple downstream applications. The adaptation is usually done by fine-tuning. Traditional fine-tuning required retraining billions of parameters. This process is extremely expensive, need months of computation on huge GPU clusters, out of reach for students, indie creators, and small businesses. Example, fine-tuning GPT or Stable Diffusion from scratch would cost millions. History and evolution. The idea of low-rank updates isn't new. It has roots in linear algebra and efficient matrix approximation. But it wasn't until 2021 that researchers formalized LoRA for large-scale language models. In 2021, a group of researchers in Microsoft published a paper introducing LoRA, low-rank adaptation of large language models. Instead of updating all parameters, LoRA freezes the original weights and parameters of the model. On top of that, it injects small, low-rank matrices into the model. This is applied to new inputs to get results for a specific use case by adjusting the weights of the original model. They demonstrated that you could fine-tune models like GPT or BERT with very few parameters, achieving comparable performance to full fine-tuning. This was a game changer for anyone without access to massive GPUs. Since then, LoRA has become a staple in AI research and practical deployment, enabling smaller teams and creators to experiment with models like Llama, Gemma, and Mistral without spending thousands on compute. How LoRA works? Let's break it down. Large language models have layers called attention layers, where the model decides which words to focus on. LoRA injects two small matrices, often called A and B, into these attention layers. During fine-tuning, only these matrices are updated. Everything else stays frozen. Think of it like tuning the strings of a guitar instead of replacing the entire instrument. You're making targeted, precise updates that allow the model to learn new patterns efficiently. Mathematically, LoRA approximates the weight update as a low-rank decomposition. That's why it's called low-rank adaptation. Instead of a giant weight matrix update, you have two small matrices multiplied together. The result? Orders of magnitude fewer parameters to train. Benefits of LoRA. The benefits are clear: less memory usage, faster training, and smaller checkpoints, perfect for deployment on personal machines or even laptops. To demonstrate, we'll use a small language model and the tiny Shakespeare dataset. we'll show how LoRA can teach a model to output Shakespearean-style text. Let's use the Jupyter Lab to run our code. First, we load the tiny Shakespeare dataset and set the base model, in this case, Gemma 3, 270 million, directly from the local machine. We split it into training and validation, then set the tokenizer. Next, we load the base model and configure LoRA with a small rank and target the attention layers. We set the rank to 4. Only these LoRA layers will train while the base model stays frozen. We can print and see the number of trainable parameters and all the parameters in the model. Then, set the data collector. Now we need to define the training arguments, set the trainer, and do the training process. Depending on your machine, it may take a few minutes to a few hours. During training, the model only updates LoRA parameters. We simulate larger batch sizes using gradient accumulation. On M2, we run the model in float 32 or bfloat 16, since mixed precision FP16 isn't supported on MPS. After a few epochs, the LoRA adapter is saved separately. This tiny adapter holds all the new knowledge, and you can load it back into the base model anytime. This is the beauty of LoRA. The base model remains untouched, reusable, and efficient. You can share LoRA adapters as small files instead of gigantic, full model checkpoints. Once training is done, we load the base model and attach our LoRA adapter. Now the model has learned new patterns, in this case, Shakespearean text. Let's just try the same thing without using the LoRA adapter to see the difference. That's LoRA in action. Tiny updates, huge impact. So why use LoRA? First, it's resource efficient. You don't need massive GPUs. Second, it's fast. Training takes minutes, not days. Third, it's modular. You can attach and detach LoRA adapters to different models. Finally, it democratizes AI experimentation, letting creators, students, and small teams fine-tune models without the cost of full retraining. LoRA also pairs beautifully with other efficiency techniques, like 8-bit quantization, to further reduce memory and compute requirements. Today, we've explored how LoRA lets us supercharge large AI models with tiny tweaks. From the math behind low-rank adaptation to training on your own laptop, it's a game-changing tool for anyone working with AI. Whether you're a curious tech enthusiast, a student, or a professional, LoRA opens doors to experimentation and creativity. If you want to try this yourself, check the links in the description for code, datasets, and tutorials. Don't forget to like, subscribe, and hit the bell to keep up with weekly AI insights. See you in the next video.